In our final video, we're going to talk about homomorphisms between groups and how they let us compare one group to another group, both its elements and the operation that ties those elements together. So again, what is a homomorphism? Well, if I have two groups, G and H, they might have potentially different looking operations. So let's call G the group with the operation dot and H has the operation circle. If those are two groups, then a homomorphism from G to H is a function that takes elements of G and turns them into elements of H. And that function satisfies for all A and B in G that the function operating on the composition of A with B gives us the same answer as the composition of that function operating on A and that function operating on B. So it looks kind of funny, but what it really means is that we get the same result by taking two elements from G, A and B, and if I look at their images over in H, let's call them 5A and 5B, that this function is a homomorphism exactly if multiplying A by B in the group G, so back in the domain, multiplying the images 5A and 5B by each other in the group H, the codomain, that the image of the product is equal to the product of the images. That's really what a homomorphism is. It really means that I can do an operation in G, or I can do an operation in H, and from the point of view of the homomorphism phi, the results are the same, either or. So in addition to that product rule, we also have a variety of other pieces of terminology that we use for homomorphisms to assign them some additional fun properties. Monomorphisms, epimorphisms, and isomorphisms. These are just statements in group language of homomorphisms that are one-to-one, onto, and bijective, one-to-one and onto. So keep in mind that these all fall into a hierarchy, that everything we're talking about here is a homomorphism. Those homomorphisms that are also one-to-one, we call monomorphisms. Those homomorphisms that are also onto, we call epimorphisms. And those homomorphisms that are both one-to-one and onto, we call isomorphisms. So monomorphisms, epimorphisms, isomorphisms, just ways of assigning additional properties to the functions underlying homomorphisms. Also, if the groups G and H that this homomorphism is connecting are the same group, in other words, if this is a function from a group to itself, we might also use an additional set of terminology. That a homomorphism from a group to itself is called an endomorphism, and a homomorphism from a group to itself that also happens to be both one-to-one and onto is called an automorphism of that group. So we have a lot of different flavors of morphism, but again, they're all just special cases of homomorphisms from one group to another group. So let's look at some examples. Here's a homomorphism that connects the group Z6, the additive group of integers modulo 6, with U7, the multiplicative group of units modulo 7. So those groups again, Z6 consists of the residues 0 through 5, and the group of units modulo 7 consists of the residues 1, 2, 3, 4, 5, and 6. So what might a homomorphism between these two groups look like? Well, sort of a naive answer might be, well, what if we just consider adding 1 to every element in Z6? Is this a homomorphism? Well, it's certainly a function from Z6 to U7. It takes 0 and sends it to 1, and 1 to 2, 2 to 3, and so forth. But is it a homomorphism? In order to investigate that, let's just pick two elements from Z6, let's say 1 and 2. If I add them together, if I apply the group operation in Z6, I get 3. Now let's look at their images under this function. Their images are 2 and 3 respectively, and if I apply the operation in the group U7 to 2 and 3, I get 2 times 3, which is 6. But notice that 3 in the domain doesn't go to the same place as the composition of 2 and 3 does in the codomain. In other words, 3 goes to 4 when it should go to 6 if this was a homomorphism. So clearly, this is not a homomorphism, and to write that in more specific language, phi of 1 plus 2 is phi of 3, which is equal to 4. But phi of 1 composed with phi of 2 would be 2 times 3 equal to 6. Since those are not equal to one another, this is in fact not a homomorphism, even though it is a function that connects these two sets. So we've got to try a little bit harder. So here's another example. Suppose I take 3 and I raise it to the power n. And that's going to be my function from Z6 to U7 this time. So just to draw out where everything goes. Phi of 0, that's 3 to the 0, is 1. Phi of 1 is 3. Phi of 2 is 9, which is congruent to 2. Phi of 3 is 6. Phi of 4 is 4. Phi of 5 is 5. So we can draw that in just by drawing arrows here to visualize this function from Z6 to U7. Is it a homomorphism? Well, let's just take another example. Let's say 1 and 2. If I add them together, I get 3. Meanwhile, 1 goes to 3 and 2 goes to 2, and if I multiply 3 and 2 together, I get 6. But this time, 6 is actually the image of the sum of 1 and 2 in the original group. So it works out. Phi of 1 plus 2 is equal to phi of 2 times phi of 3. And in fact, it also works in general. Phi of n plus m is indeed equal to phi of n times phi of m. So this is a homomorphism from Z6 to U7. And in fact, because this is 1-to-1 and onto, this is in fact an isomorphism from Z6 to U7. So Z6 and U7 are in fact isomorphic as groups. And we would write that as U7 congruent to Z6. So when we write it that way, we're saying that there's an isomorphism from one group to the other group. Here's another example. Let's take the group which is the cross product of Z2 with Z2. We call this a Klein 4 group. And here's an example of a monomorphism from that group into the symmetric group on 4 symbols. It takes the element 1, 0 and sends it to the transposition 1, 2, and it takes 0, 1 and sends it to the transposition 3, 4. So the first thing we have to ask is, in what sense does this actually define a homomorphism? Because I've only said what it does to 2 elements of the Klein 4 group on the left, when in fact there are 4 elements that I have to figure out what happens to them. So we've said 1, 0 goes to 1, 2, and 0, 1 goes to 3, 4. So is this enough information to define a homomorphism into S4? Well, sure. Because where does the identity have to go? Well, every homomorphism sends the identity element of the domain to the identity element in the codomain. So 0, 0 has got to go to the identity permutation. And likewise, because of the product rule, 1, 1, because it's the result of combining 1, 0 and 0, 1 with the operation in the Klein 4 group, its image in S4 should be the same as the composition of the images of 1, 0 and 0, 1 in S4. So the composition of 1, 2 with 3, 4, that image had better be 1, 2, 3, 4. So this is indeed a homomorphism. And in fact, the image of this homomorphism is the subgroup that we were looking at before, the subgroup H. So this is a 1-to-1 function for sure, because the different elements in the Klein 4 group have different images in S4. But it's not onto, because there are a whole bunch of elements over here in S4, such as 1, 3, that are missed. They're not getting hit by an element from the Klein 4 group here. So it's 1-to-1, but it's not onto, so this homomorphism is a monomorphism. Now let's look at an automorphism of the dihedral group with a square D4. We're going to define it by taking every element of G and just multiplying it both on the left and the right by the transposition T. Remember, that was the horizontal reflection of the square in the group D4. So there are 8 elements in the group D4. Here they all are. And this function is going to take each of those 8 elements and send it to perhaps a different one of the 8 elements in D4. And just by working all of these out, we can find out where each of the elements goes. So phi of the identity is the identity. Phi of R is really R cubed, according to that arithmetic. Phi of R squared is R squared. Phi of t is equal to t. Phi of tr is equal to tr cubed. Phi of tr squared is tr squared, and phi of tr cubed is tr. So we can just work those out again using the properties of the elements of the group D4. Here's a proof that phi actually is a homomorphism, phi that's defined in the way that we have defined it here. Well, to prove that, we just need to show that the product rule is satisfied. So let's take 2 arbitrary elements in the domain D4. We need to show that if I apply phi to their product, gh, I would get t times gh times t. I need to show that that's the same thing as I would get if I take phi of g and phi of h and then compose them together. Well, phi of g is tgt, phi of h is tht, and then just simplifying this product using first the associative property in a group by getting rid of the parentheses and grouping them around t's. Then t squared is the identity, so I have tght. We found out that indeed phi of gh is equal to phi of g times phi of h, and therefore phi is indeed a homomorphism from D4 to D4. So that makes phi actually an endomorphism of D4. Why is it an automorphism? So we need to show, in order to show that phi is an automorphism of D4, that it's an isomorphism, that it's both 1-to-1 and onto. To show that it's 1-to-1, let's suppose that phi of g and phi of h are the same thing. In other words, phi sends 2 elements g and h to the same place. Well, that means that TGT is equal to THT. And by multiplying on the left by T, and then multiplying on the right by T, we find out that implies that G, in fact, is equal to H. And so we've proven that if phi of G is equal to phi of H, then G is equal to H, hence phi is 1 to 1. Now to prove that it's onto, we need to show that every element in D4 is getting hit by some A. So we want to show every G is equal to phi of some A. Well, that would be the case if G is equal to T times A times T, but then multiplying again on the left by T, and on the right by T, we find out that the element A that hits G is just TGT. So let's check that that actually works. Phi of TGT is T times TGT times T, but since T squared is the identity, we have verified that phi of TGT is equal to G. Therefore, every G is getting hit by an element, namely TGT. So we've shown that this phi is in fact an automorphism. It's an isomorphism of the group D4 with itself. We've actually shown a little bit more than that. We've shown that this particular automorphism is its own inverse. Why? Because G is getting hit by exactly TGT, which is phi of G. So phi of G is equal to G. So where does this leave us? We've looked at subgroups of a group as just being smaller groups located within larger groups, using the same operation and having the identity, closure, and inverses inside of that smaller subgroup. We also looked at cosets. Cosets were just the result of taking a subgroup and shifting it by multiplying it by a fixed element from the bigger group G. And then finally, we looked at examples of homomorphisms, being functions from one group to another group that not only compare the elements, but also compare the operations in those two groups, and the various flavors of homomorphisms, monomorphisms, epimorphisms, automorphisms, endomorphisms, and isomorphisms that we can have as well.